So, we have been talking about fault models. Okay. So, in particular we talked about the single stuck-at fault model. And how for a combinational logic we can use the theorem, right, the fault compaction theorem, to eliminate equivalent faults and dominant faults. Okay. So, the theorem says that if you give me a combinational logic with some primary inputs and there are some fan out branches here inside. So, consider the faults, single stuck-at faults at Pi or the primary inputs and the fan out branches. So, this is enough. Okay. So, we will go back to the example. So, the theorem says that it is enough to consider the fan out branches and the primary input. So, I am starting with the primary inputs and then I am going to look at the fan out branches. The other faults are either equivalent or dominant and can be eliminated. Okay. And like I said earlier, some more equivalence can be observed, right. For example, the stuck-at one fault here and the stuck-at one fault here are same. So, I can eliminate that also, right. Similarly, the stuck-at one fault here and the stuck-at one fault here are same. So, I can eliminate this also. In the same way, there is an AND gate, the stuck-at 0 and the stuck-at 0 are same. So, we can eliminate this also. So, we have brought it down to 1, 4, 5, 7, 8, 9. So, 9 faults. So, label these guys. I think we had called this E and F and G, and this was called H. Okay, so, H1 and H2. So, our list of faults is A0, A1, B0, B1, C1, okay, then D0, D1. And H11, H10 and H11, H10 and H20. Okay. So, A0 and A1, B0 and B1, C1, then D0, D1, H10 and H20. Okay. So, we have to find a test vector or a way to test each one of these faults. Okay. So, we will start with A0. I have taught you one sort of way to find a test vector for A stuck-at 0, and that was based on that XOR gate method, right. What does it say? The circuit's normal functionality is P plus C, BC. B dot C is the output of the AND gate here, and we are adding it to A, and then B C plus D. Okay. So, this is B C plus A and this is B C plus D. So, this is a good circuit behavior. So, the faulty circuit, when A0 is present, will produce A will become 0. So, it will produce BC dot BC plus D, right. So, somehow we have to make sure that these are different. Okay. So, we have to make sure that G XORed with GA0 must be 1. So, select A, B, C, D, right. So, let me write it down again. So, we can try the XOR method, no doubt, but I will teach you a slightly easier way. See, what is the fault we are considering? We are considering the fault A stuck at 0. What should I apply at A, right, which will make sure that the two are different, G and G of A0 are different. See, the fault is A is stuck at 0. So, if I apply a 0 here, it is no use, right, because it will cause both the faulty and the good circuit to behave in the same way. So, we have to somehow distinguish. So, we should say, look, a good circuit should have a 1 and a faulty circuit has a 0. So, that is what we need to do. And at the output also, somehow we should distinguish the good and the faulty circuit must have different values. Only then it becomes a useful test. Otherwise, both the good and the faulty circuit are behaving identically. Now, if I put 1/0, it means a good circuit I am able to put a 1 properly, but if it is a faulty circuit, it has a defect. As a result, it sees a 0 here. Now, what should I put here so that the effect of this fault goes out? See, after all, we cannot directly look at this value, right. I can't put a multimeter here and check what is the value here. I had to observe it only here. So, this is the observability point. So, the effect of the fault must be propagated. For that, I had to control this value. If I put it as 0 here, then the fault gets propagated further. If I put a 1 here, unfortunately, both the good and the faulty circuit will produce a 1 here. Okay. So, I must put a 0 here. If I put a 1, it will kill the fault, it will not let the fault get propagated. Both the faulty and the good circuit will produce a 1. So, I will put a 0 here. That will cause the output to become a good circuit will produce a 1, a faulty circuit will produce a 0. In the same way, if I want to propagate the this fault to the output, okay, then if I put a 0, I am going to kill it, right. Output will become 0 no matter whether the circuit is a good circuit or a bad circuit. So, I have to put a 1 here. If I put a 1, then the good circuit will produce a 1 and the faulty circuit will produce a 0. Now work back. If I want to put a 0 here, what should I put here? I can put 0 here, and this is as of now do not care, or I could put x here and 0 here, either of these is okay. And in order to put a 1 here, then because I have made this into a 0 by putting a 0 in one of these, this will have a 0. See, this 0 will come here also. So, I have no choice but to put a 1. So, the A, B, C, D choice, I had to make a 1 here, I had to put a 1 here, okay. And B and C, I have a choice, I can make it x0, oops, sorry, I can put x0 or 0x. So, I have these choices for tests. So, 1x01 or 10x1. So, in other words, 1001 is a valid test vector, 1101 is a valid test vector, 1001 is already covered. So, no need to mention it again. So, 1011 is also a vector. So, I have 3 vectors. What is a test vector? If I apply 1001 here, if I apply 1001, then this fault has been activated, okay, because the good circuit will have a 1, but the faulty circuit will have a 0. We call this as fault activation. Okay. If I simulate, I will get a 0 here, and 0, and if I simulate, a good circuit will have a 1 0, 1 plus 0 is 1, a faulty circuit will have a 0 plus 0 as 0. Okay. So, you will realize that 1001 is also okay, or 1101 is also okay, or 1011 is also okay. So, any one of these will result in a 1 at the output if the circuit is good, a 0 in the output if the circuit is bad. Okay. So, 3 vectors and the output is 1 for good circuit, 0 for faulty. So, once again remember that if I apply one of these test vectors and if I observe a 0 at the output, it does not mean that A is stuck at 0. It could be one of the causes, right. The actual reason could be that G is stuck at 0, okay, or it could be that the it could also be because this guy is stuck at 0, F could be stuck at 0. So, there could be a more than one reason why the output G becomes 0. One of them is A is stuck at 0. That clear? Yeah. Let me do one or two more exercises. So, I had a OR gate like this and I had an AND gate like this. Let us try H1 stuck at 0. So, H1 stuck at 0. We are trying to generate a test vector. So, first thing is step 1, activate the fault. So, what does it mean? I must place a value on H1 which is different from the faulty value. The faulty value is 0. So, I must put a 1. So, it should be 1/0. So, 1/0 is interpreted as a good circuit has a 1, the faulty circuit has a 0. In order to put a 1 here, we have no choice but to put 1 here. If I apply B and C to be 1, then I will be able to put a 1 here. The next thing is to propagate the fault. To further send the effect of the fault to E, I have no choice but to put a 0 here. If I put a 1 here, then both the good and the faulty circuit will get a 1 here. So, if I put a 0, then a good circuit produces a 1, the faulty circuit produces 0. And in order to produce a the fault at the G value, the fault needs to go all the way up to the output. I have no choice but to put a 1 here, right. If I end up putting a 0 here, G will be 0 no matter whether the fault is present or not. So, as a result we have to put a 1. For that reason we have to put a 1 here. Actually it is see this is x actually, we do not we can either put a 0 or a 1, because this 1 will also cause a 1 here. Remember there is no fault on H2. So, a 1 on this will come over here, okay, and as a result this is x. So, the test vector is 0 1 1 x. That means I have 0 1 1 0 is a vector and 0 1 1 1 is a vector. So, both will work, and in either case, right, the good circuit will produce a 1, a faulty circuit will produce a 0. So, we have looked at two things. Step 1 is fault activation and step 2 is fault propagation. Yeah, very important. Let us do one more exercise so that you can understand it one better. So, let us try this is a very symmetric circuit. So, let me try making a small change. Okay. So, I have made a small change. So, once again by our theorem we had to use these faults. Okay. So, I took the fan out branches and the primary inputs. We can eliminate this guy here because in an AND gate the two input stuck at 0 faults are equivalent. Similarly, if I use stuck at 1 here, I think I made a mistake. Stuck at 0 must be eliminated. Okay. So, stuck at 0 here is same as stuck at 0 here, they are equivalent to each other. In the same way, stuck at 1 here is equivalent to stuck at 1 here. So, we need not consider this guy. Similarly, see the stuck at 1 here and the stuck at 1 are here are same, and the stuck at 1 here is equal to stuck at 0 here. So, I should be able to eliminate this guy here. Okay. So, it is an inverter. The stuck at 1 output at the yeah, stuck at 1 output at the stuck at 1 fault at this input is equivalent to the stuck at 1 fault. So, I can eliminate the stuck at 1 fault here, but that is the same as a stuck at 0 fault here. So, I eliminated the stuck at 0 fault here. Okay.